So we saw the series for cosine of x. But we didn't derive it. So the formula is, I'm going to write it over here because I want to write the derivatives over on that side. So if we recall, the formula for the series is the sum n equals, this is the general formula, not the formula for this specific case. N equals 0 to infinity, the nth derivative of f evaluated at alpha, which in this case alpha is 0, over n factorial x minus 0 to the n, which I guess the way I wrote that previously was just x to the n. X minus 0 is just x. And if you recall, the formula that I showed you for the cosine MacLauren series had two n's in it instead of just n. So we'll get to how that comes into play later. So the first thing that we do when we're trying to derive one of these series is we want to look for a pattern, if possible, for what the terms of the series are going to look like. So we're going to take cosine and find its derivatives. The 0th derivative, that just means the regular function without any derivatives at all. So the 0th derivative is cosine of x. And then if we evaluate at 0, because we're doing the MacLauren series, so we're evaluating at 0, this is cosine of 0, which is 1. Next, the derivative of cosine of x. So the first derivative is negative sine of x. I always pause because I have to think about what the graphs look like. Right, so it's cosine goes down, yeah, negative sine. Okay, so that means that the first derivative, evaluated at 0, is negative sine of 0, and sine of 0 is just 0. So we'll keep doing this until we feel like we have a nicely established pattern. The second derivative is, well, the derivative of sine is cosine, but we have this negative hanging out in front, so negative cosine of x. And then if we evaluate this derivative at 0, we're going to get negative cosine of 0, which is negative 1. And then we will see that this pattern repeats. The third derivative is negative sine of x, so we end up with sine of x. So sine of 0 equals 0. And then the derivative of sine is cosine. And so on. So you could check what I'm going to claim is true by doing more terms of this series. But what we see is that the odd terms all have a sign in them, sine of x or negative sine of x. But it doesn't matter because those just are equal to 0 either way. So odd terms are 0. And then the even terms they're going to switch back and forth between 1 and negative 1. So the even terms go back and forth between 1 and negative 1. Because you're going to have positive cosine, then negative cosine, positive cosine, then negative cosine repeated. So, if we want to write our series, the problem with plugging something like this into our series is that it gets really complicated if we have two different patterns going on here. One pattern is the pattern for the odd terms that are just 0, and the other pattern is the pattern for the even terms where we flip back and forth between 1 and negative 1. So we kind of manipulate the series a little bit just so that we can focus only on the even terms. This camera is really funky because it shows me a mirror image, so if my hair is sticking out on the left, sorry, anyway, don't bother editing that out, it's okay. So we have this problem where we have two different patterns, one corresponding to the odd terms, one corresponding to the even terms. So what we want to do is we can ignore the odd terms. They're all just a coefficient of 0, so 0 times x to the n is still just 0. And we're just going to look at the even terms. So if we looked at 2n instead of just n, we know that 2n gives us all of the even numbers. So if n is 0, 2n is 0. If n is 1, 2n is 2. If n is 2, 2n is 4. If n is 3, 2n is 6, and so on. So by just saying 2n instead of n, we're going to just consider the even terms. So that's what we want to do. And this will give us all of the even integers. So we're going to take that idea and we're going to look at the sum from n equals 0 to infinity of, and then we'll have the coefficient here, x to the 2n. So I'm putting x to the 2n because this is just going to give us the even degree terms, which is all we need. So if we look at x to the 2n, we have to make the factorial agree with the exponent. So x squared, we want it to have a 2 factorial on the bottom. X to the 6th, we want it to have a 6 factorial on the bottom, and so on. So what we do is we make sure we do 2n factorial. And it is very important that you put these parentheses in here. Some people forget, but 2 times n factorial is very different than 2n factorial. It is significantly smaller without the parentheses. And then on the top, we saw that the even terms start with 1, then go negative 1, positive 1, negative 1, positive 1. So if we do negative 1 to the n, then this this 1 is going to flip-flop between negative and positive 1, because negative 1 to the 0 is 1, but negative 1 to the 1 is negative 1. So if you raise negative 1 to an even power, you get positive 1, and if you raise it to an odd power, you get negative 1. So by putting negative 1 to the n, we're capturing this idea that we go between 1 and negative 1 for every other even term. So this is how we end up with this for our Taylor series for cosine of x. And I'm going to write that this equals cosine of x, because it does. You can't always write that a Taylor series equals the function. You can only do that if the radius of convergence is infinity in that chart that you have. But yeah, in this particular case, it does mean that the Taylor series, if you went to infinitely many terms, you would get exactly the cosine function for this.